All right, and I am finally back. I know that this seemed a little bit weird given I published a video yesterday, but now it counts as me being back. I've basically I just finished as of I guess about an hour ago. I finally finished submitting the last of my work that is due in for the end of this term. I've got a meeting with someone at 3 o'clock, I think, maybe. Should probably check that. I should. That should be some information that I can call to hand. The point at which I'm meeting one of my teachers. But okay. Aside from my slight not having any clue what's going on in my life, yeah, I'm basically done for this term now. The holiday's going to be stressful. It's going to be painful. It's going to be quite awful. But that is a problem for future Ninja to deal with. For now, I am vibing incredibly hard, and I decided, what better to kill the vibes than dying in hardcore battle devastation attempts. Okay, let's hope that lag clears up. This is a little bit sketch. Vaguely slideshowing. No, it's not really. Slideshowing, I mean. Exaggerating significantly. Don't have the item ID for healing cherries on me. Let me get up the database browser so I can get that fairly quickly. Yeah, I'm really I'm in a very, very good mood. Was up to like probably 2 a.m. last night after spending ages working with a friend, just going through the programming exercises. It's weird because the programming exercises are honestly incredibly simple. I mean, I've got a fair amount of still all programming for physicists, which is very different to actual programming, but I've still got a good amount of programming experience, and I did a computer science course in first year, which is, so yeah, I did about a quarter of the computer scientist course in first year. I don't know how much that exactly means to everyone, but it's basically a quarter of the Pierre Komsky course. But yeah, so I'm fairly experienced with this, and so it's this shouldn't be taking me very long, and because it's physics programming. Physics programming is easy. However, unfortunately, I'm really, really bad at reading unmotivated instructions to get me to do a task. I don't know if anyone else has this, but it's if I know. So I remember the perfect example being in chemistry years ago. I remember we'd have a complete guide on how to perform the experiment, and I would just be the steps would be individually kind of quite simple, but they'd kind of all interlink, and if I were doing it step by step, it would take ages because I wouldn't be preparing for the next step whilst I was doing one. Whereas the second I knew exactly what reaction, what series of the second I knew the theory behind what we were doing, it was wait a second. Okay, I know what series of reactions we're doing. I kind of know what we're going to be doing in advance. I can do this a lot faster. And I remember that as being a fairly significant a significant effect in changing how long it would take me to do any particular project or any particular thing, just reading from instructions. And the same thing with physics practicals last year and first year as well. Just anything where it's now do this, now do this, now do this. And without much reasoning or without a clear idea of the whole thing that's going on, I'm just incredibly inefficient. And so it was a very similar thing with the programming exercises. It was all very, very simple. Once I was kind of very happy with what I was doing and had a plan in my head for how I was going to do it, the hardest bits of code I had to write took me maybe half an hour. But it was just the working out, okay, what various things, what's capabilities does this program need? How much am I going to need to generalize it? So, for instance, one of the things was looking at a harmonic oscillator, and the question being, okay, what actually... Let's not die. What actually do I want this to be, this function to be able to do? Because, so I needed to have a function that would... that's not good. That's not good. Keep moving. There we are. I need to have a function that would be able to solve a differential equation describing, an equation of motion for a system. And it's like, okay, that's already built in to the library I'm using. Like that's already a function. So if I'm going to solve... Why am I like this? I really should have just de-aggroed the spiderling. Okay, this will be fine. Can run and jump you. There we are. And that's a little bit better. Okay, cool. Pretend I didn't... And yeah. Given that I de-aggroed the spiderling now anyway. Don't know what the point of all that was, but anyway. Let's have you in a position where I'm not just going to de-aggro you by accident. And here we go. Yeah, it's like the individual things didn't take me any time, like, at all. But it's just like, yeah, so I was considering a problem where I had to solve an equation of motion for a system, and it's like, okay, in order to solve the equation of motion, I need a function that defines the equation of motion. But how general should I make that function? And it's like, well, I can think of, like, so many degrees of generality I could write that program in, and it's going through the entire thing, working out, okay, what am I going to need for all the later bits? Why am I like this? Let's de-aggro one of those guys. Well, let's de-aggro both of them and then re-aggro one. I don't know. But anyway, regardless, it is done. It is done, and I am a very, very, very happy ninja. The sun is shining outside. It is a beautiful day. It is significantly nicer than it has any right to be, given we're in March at the moment, and we're in the UK. The vibes are exquisite. I also actually, the other day, I had to give a presentation based on so for part of our course, I've mentioned this in the previous video, we're basically, part of our course, we go through and review some research. We review like a field in research. I'm doing my review on Quasi Crystals, and we need to basically give a presentation on this. And I'm dead. I knew I was playing risky, but well. Yeah, we basically, we had to give a presentation of this, and basically, yeah, the reason I have been stressed as heck for the past couple of days was the fact that we had our presentation. I was planning on having about a week to do computational exercises, then get this presentation done after that, and, you know, everything would be good vibes. Turns out what actually happened was our person finally got in touch with us about the presentation a few days before it actually happened, and so I had to do that in parallel with preparing for doing the computational exercises. It's fine. They all happened. Right, that felt weird. Felt like my jump there was weird. I don't know if someone can look back and tell me if it was. But yeah, so yeah, I had to give a presentation on Quasi Crystals, which I think is a really, really, really cool topic. So basically, well, at least let's not die to the Stromlings. Yeah, okay, I deserve to be smashed here, honestly. With plays like that. There we are. It was so bad. Yeah, so basically I have to do a research review on Quasi Crystals, and basically the thing I'm really interested in is, okay, we've got this notion of a Quasi Crystal, which is basically, it's something where you've got long-range order, which is what you classically expect from a crystal, but it's a little bit of a prank because you don't just have long-range order, you also have this... Oh, you don't have long-range order like you normally expect. Normally when I say crystal, the thing that will spring to mind for anyone who's studied crystallography is like a regular repeating lattice. Maybe you'll see an FCC crystal lattice, maybe you'll see just a simple cubic lattice. Doesn't really matter. The important point is it repeats. And basically, it was discovered in like the 1980s, I think, that, well, Roger Penrose actually significantly before this, Roger Penrose came up with a tiling known as, well, the Penrose tiling, and it basically, it's a really interesting tiling because it is completely periodic, it completely tiles a plane with a finite number of tiles, a finite number of tile shapes. In fact, just you can make ones with just 2, although the original didn't. But it never repeats itself. And so it has long-range order, as in you need to know a negligible amount of information. You need to have information about a tiny number of tiles compared to the complete set of tiles to completely describe the system. There's a more mathematically rigorous way of phrasing that. But basically it's almost completely determined by like a tiny proportion of the tiles. In fact, as the crystal gets larger and larger, the proportion of the tiles which completely uniquely determine it tends towards 0, which is pretty cool. So in other words, we've got long-range order, the kind of long-range order we're used to in periodic structures, but this tiling is not periodic. It never repeats itself, but it still tiles the plane. And so it also has a very cool property, which is that it has 5-fold symmetry, and you can't tile a plane periodically, and it's a really easy mathematical proof. You can't tile a plane periodically with anything that has 5-fold symmetry. So the question is, so a question Penrose got regularly asked is, okay, you've designed something like this. Could this ever appear in nature? And his reply was like, yes, but why? Why would it ever appear in nature? Like in theory? In theory, yeah, sure, there's nothing against the laws of physics that prevent atoms arranging themselves in this very particular way. But do they have any reason to? We have a good reason for getting periodic order. Do we have any reason for getting this kind of order? And basically, now it had never been seen. So people were like, and he wasn't coming up with this from the point of view of saying, we're going to get crystals which do this. Penrose was a mathematician, so he wasn't doing it for anything like that. There was no aim for this to be physically realizable, or okay, like it was physically realizable. You could cut out tiles and put them in this pattern, but there was no aim that this would ever be something that would be replicated in nature. However, it turned out it was discovered by Shexman that it was, and it's like a classic bit of the scientific community being utterly awful. He was basically ridiculed for, he found a diffraction pattern which exhibited, the diffraction pattern exhibited 10-fold symmetry. 2 of those, the reflectional symmetry is actually related to the fact that we measure, what we measure, so we tend to measure intensity. Which involves squaring stuff, and yeah, if I recall correctly, that's what gave rise to the 10-fold symmetry rather than the simple 5-fold symmetry. I would have expected knowing what the crystal looks like, but it doesn't really matter. The point was we had suddenly evidence that, wait a second, this thing that, like, we've got something that looks like a crystal, but like it has very, very clear points in its diffraction pattern. That's characteristic of a crystal, but the diffraction pattern's a fractal. And it's also got a symmetry which should not be allowed. Like, if I tell you, go take... so if I want to find if I would have a diffraction pattern of, say, 6-fold symmetry, I can hazard a really good guess as to how I might form one. What I'm going to do is I'm going to take something with 6-fold symmetry, and I'm going to attempt to tile a plane with it. So, for instance, I will take a hexagon, and I will attempt to tile a plane with it, and, hey presto, I'll find that, oh yeah, that does actually give me something with sixfold symmetry. Nice. But the issue is, if you try and do that, and I'm slightly well, this is. I don't know how rigorous this is as an argument, but there are very, very easy rigorous arguments to make for this. But I just need pen and paper to draw them out. I hope I'm recording all of this. I am playing so incredibly badly today, but don't care because I'm in a good mood. Yeah, if we wanted to describe, yeah, if we wanted to come up with something, then we'd base it with fivefold symmetry, then it would make sense to start with pentagons and try and tile a plane with them. However, the thing is, what you will find is if you try and do this, and it's not a bad thing to try and do in your head, well, you'll find you can't even fit, like, if you just take a single corner of one pentagon, and you try and fit, in order to tile the entire plane, you must be able to fit pentagons around that one pentagon without there being any gaps. And if you try and do this, you will find almost instantly that you can't do it, because what are the interior angles of a pentagon? I don't remember. It's 108 degrees, I think. I think it is. But yeah, you'll find that if you try and divide 360 by 108 degrees, well, it doesn't divide evenly. You would need a non-integer number of pentagons to cover that gap. You basically, what would happen is you'd get 3 pentagons, they'd fit in, but then you'd be trying to fit in a 4th one and it wouldn't fit, but there'd still be some gap. And so you can't tile the plane with pure pentagons. You can then try and come up with other shapes, but it turns out, if I recall 100% correctly, yeah, no, it turns out you cannot tile the plane with fivefold symmetry with a single shape. I'm pretty certain that last bit holds. I'd have to be a little bit more careful were I to make a fully rigorous mathematical proof, but no, I'm pretty certain I'm right on that. And so the point is, these crystals were theorized, and then people actually found one, and Schechtman found one, and he got utterly destroyed by the scientific community for like ages. They were like, oh, stop showing me these diagrams, these diffraction patterns, which were like very clearly showing this tenfold symmetry. They're like, it's just a result of twinning. Twinning is a type of defect you can get in crystallography. I have absolutely, like, I'm no expert in crystallography. I'm fairly good at, like, mentally working out diffraction patterns. I'm confused as to, maybe twinning could give rise to it. I don't instantly see how, because, like, you do need some fivefold symmetry, and twinning wouldn't give rise to, like, actually global fivefold symmetry. But maybe it could give rise to local fivefold symmetry. Maybe it could make what's known as an approximant, which would have a diffraction pattern somewhat similar. But regardless, he was basically laughed at for saying that these quasi crystals existed until, I think it was Steinhardt, found a meteorite, which also had quasi crystalline behavior, and people were like, oh wait, shoots, maybe we were wrong. And then eventually he got the Nobel Prize for this discovery. Sorry, the reason I'm not moving around is because I'm was speaking and confusing myself at the same time as I was going to give myself 100 cherry blasts. Of course. Okay. So yeah. And yeah, so the interesting thing about quasi-crystals is the following, which is the fact that how do we describe them? How on earth can I come up with a description of a quasi-crystal? These things don't have periodicity. So how on earth can I... So, like, the standard ways that I would analyze crystals. So let's just take your classic example of analyzing analyzing the conduction properties of a crystal. If I... Like, the standard way I would do that... and like the way you get taught in undergraduate physics is like, yeah, we're gonna like use and abuse something known as the nearly free electron model, which basically gives us some notion of where we're going to have electrons, it turns out, can't have certain energies, basically. In a crystalline lattice, this is... and the energies they can and cannot have, or more specifically, the energies they can have, there are certain continuous regions of these energies. These are known as bands. And the spots where there are no energies are known as band gaps. These band gaps are they are incredibly important. They're what make those are literally what define semiconductors. A semiconductor is something where, without thermal energy, you have a band gap, but the band gap is small enough in energy that if you do have like some reasonable thermal energy, which is like 25 milli-electron volts, at room temperature, say, then it becomes electrons can hop over the band gap and become conducting, hence semiconducting. And so, like, if you're doing the model which gives rise to this, and you're doing the maths for it, one of your like first assumptions is that you have periodicity. Specifically, you will write your system in terms of a Fourier series. Fourier series only apply if you're periodic. Simplest summary of a Fourier series is basically it's the answer to the question why trumpets sound different to violins. Or what makes it's also kind of the answer to the question what makes a note sound pure. It's a notion. It's a like brightness. So I remember looking at trumpet mouthpieces and going down a little bit of a rabbit hole of, okay, how would one design a trumpet mouthpiece? And like various things which are attributed to the mouthpiece, but also the shape of the instrument are notions such as the brightness of a sound. And what does brightness of a sound mean? Well, it more or less. So we've got to answer that, we need to use Fourier series. And basically, these are a really, really cool mathematical entity, or a mathematical idea. Basically, Joseph Fourier was working on the problem of solving the heat equation. We knew how heat flowed, and we had a partial differential equation expressing the flow of heat. However, we also couldn't solve it. We didn't have a solution which described it. Or at least, I don't remember if we did. I think he was looking at the problem of heat flow on a ring as well, which is a slightly different. I think we probably did have a solution to how heat flowed, because that's just a Gaussian, and someone would have guessed that as a solution. So if I recall correctly, he was more specifically looking at heat flow on a ring. But basically, yeah, Joseph Fourier, interested in heat flow, comes up with basically a really neat theorem, which is that a certain set of periodic functions are sufficient to create, using a linear combination of them, i.e. just adding them up, they're sufficient to create any periodic function, which is really interesting. In particular, the basis Fourier chose, or the set of periodic functions Fourier chose as being sufficient to describe every other function, were... There are lots of periodic bases that he could have chosen, but the one he did go for was that of sinusoids and cosinusoids. So these are what we would tend to think of as pure notes. So if I were to sing, you would be able to very easily tell the difference between me singing a particular note and like a signal generator doing a particular note. The signal generator, I mean, I'm going to have to sing both of them, but the signal generator doing a particular note would be something like... Whereas me singing particular notes might be like la. Sorry, okay, let's actually hit the right note, but it'd be something like la. I think I actually just did basically the same thing but different volumes. Well, one of them I had my lips closed. But anyway, the point I'm trying to make is that those two things sound different. I also, wait a second. If I really want to make this point better, we might have something like So that was played on the first one played on a recorder, second one sung, obviously well hummed actually, but again lips closed. But the important point being that those were distinctive despite the fact they were the same note. So what actually sets them apart? Well, what sets them apart is the first one's much closer to a sine wave. And basically what this means is that the first one, it was that the, actually, let's say I try and write out the first one had a certain, it's a note, pitch corresponds to frequency, therefore it had some frequency associated with it. Let's assume it's a pure sine wave. Doesn't actually have to be for the maths to work, but it's a lot easier to do all the maths with sine waves, and that's why Fourier did it with them. I don't know what happened to the loop there on this guy, but it's fine. And so what basically you can do is you can say, okay, I'm going to take this basic note, I'm going to take this this basic sine wave, say played on my recorder there, and what I'm now going to do is I'm now going to layer it with the same note. Let's say a fifth up. I don't play the recorder, so I have no idea what a fifth is off the top of my head. So I'm just going to try and work it out. Sorry, did a perfect fifth, and then it's like, okay, Lego Universe theme time. So that was a. So the three notes I played at the end there, one of those was just a bass note. I have no idea what was I playing. It was. I mean, I literally. I can only play the recorder by ear, so I have no idea which notes I'm actually playing. And I started on a scale I didn't know, or that I'd never played in before. So that was all like me trying to work out the notes. But yeah, the point I'm trying to. What am I doing? What am I doing? Oh. The point I'm trying to make with this is, so those three notes that I played right at the end there, the la 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 la, those are three harmonics, basically one of those notes can be seen as the I guess I don't know what the term is, just the lowest harmonic, and then the others are harmonics of that. What this means is that they all repeat over the same time period. It's just that the first note I did repeats once over the time period. It's the base of that note. I don't know what it is. It'll be on the order of a couple of hundred hertz. Then the second note would repeat twice over that period, and the third note would repeat 3 times over that period. But what that means is those do all have the same periodicity as the first note. They just, also the later notes just also have even more periodicity. But what that means is if you add them up, you're going to generate a function which has the same period as the first note. And so that's the chords that we'd get from that. That's, I think just having a tonic and a fifth, that's just known as a power chord. Quite often used in, I think like rock, etc. I don't know. No expert on music theory. But the point of that is that we add those all up, and those form like a nice chord. And part of what we think our brain interprets as nice is like how similar the periodicities are. It's a little bit dubious, but if you keep going up, if I were to keep adding notes to that, so I really should start low if I were going to try this. And why am I trying to do this whilst fighting Merkel Bloch and singing? I don't sing. So if I were to begin low, la, let's just find a low note I'm comfortable with hitting. La, la. I'm not going to try this, actually. I cannot concentrate enough to sing chords accurately whilst fighting. But basically, you can find out, and it's lovely, because I played a trumpet, and this is just all so clear on the trumpet. Sorry, I told a lie before. Those notes were not... When I played the la, 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 those three notes, they're not... they don't all have the same underlying periodicity. I'm misremembering. So had I started an octave down, then done those series of notes, then they would all have had the same periodicity, and they would be 1, 2, 3, 4. The first to the fourth harmonic. However, the way I sang them, I was just doing 2 to 4, and therefore the first and the last note that I originally sang, those would still have the same underlying periodicity. They'd still have the same, or they would still both repeat with the same frequency, but the one in the middle wouldn't. But anyway, the point of all of this, and the reason I'm discussing all of this, is that basically what Fourier says is me singing a note, well, that corresponds, let's say I sing an A, 440 hertz. All that's telling you is, all that 440 hertz is telling you that's about the lowest harmonic. That's about the periodicity with which I'm singing, or with which the periodicity of the note I'm singing. It says that if you repeat it by anything, that, yeah, this will, that the sound wave I'm making repeats 440 times in a second. Note this also means that it repeats 220 times in a second. Also means it repeats 110 times in a second, and obviously could keep subdividing that. And so what this means is that despite the fact that I'm obviously playing a different sine wave to the same notes when I play the recorder, that it still has the same frequency. And so how can we do this? We can build it up with other notes that have, so if we're dealing with a concert at A, 440 hertz, that would correspond, we could also have things added over the top of that, which are 880 hertz. Because that would still repeat. If something repeats 880 times a second, then it's necessarily also repeating 440 times a second. And so basically you can add those two up, and hey presto, you get something which it's still the same note, but it sounds different. Really cool. And this is how it's part of how you can make synths. You can basically do this. But anyway, this is such a huge tangent from crystallography, but the Fourier series are like an incredibly important notion in physics. They're really, really deep. And so yeah, what are we doing with these Fourier series? So basically, the notion is that what changes the sound is the distribution of these harmonics. What separates my voice from the noise made by a recorder is the fact that, well, I typically have a lot of higher harmonics than a recorder, the recorder tends to have a much kind of simpler spectrum. And when I was looking at trumpet mouthpieces and how you design those, one of the terms which would come up regularly is like, okay, this is bright. And so what does bright correspond to? Well, what that corresponds to is the fact that I have lots of higher harmonics, and they're quite intense, or they're quite strong compared to the like bass harmonic. Bass. I don't know the term I'm looking for with this. The lowest harmonic is more or less the word I mean to use. Probably aggroed 2 stromlings, I think. I don't know, probably 3. Let's just try and get that one if I can. Ah, no. Clumps, that's annoying. Let's not get stuck on this spot. And that stupid peel. Oh, yeah, that's fine now. It should be anyway. So many things shooting at me, but that's all fine. Got rid of most of them. Oh, we've gotten rid of the pirates that are aggroed. Now we can just take these off one at a time. Nice. Okay. So yeah, that's what makes a trumpet bright. That's what sets apart, for instance, the flugelhorn from the trumpet, say, which is that's what changes the tone. The shape of the bell determines. Actually, I just realized I know a lot more of the maths for this than I kind of expected to. Or I can interpret this a lot more. So the flugelhorn has a much what sets it apart from the trumpet, like valves, etc., the same, you can play it on the same mouthpiece. What really sets the two apart is their bore. In particular, this is similar with the cornet, but the trumpet and the flugelhorn are just like more extreme. The cornet is somewhere in between. The thing with the flugelhorn is that the bore continuously increases in size. It's getting wider from much earlier on, and it keeps getting wider for longer. What this means is it's effectively related to there's at some point going to be a cutoff where the air is no longer in the horn and is in the surroundings. And basically, that cutoff, how sharp that cutoff is, helps to determine how many higher harmonics we have. At least spatially, actually, it's going to be more complicated in the frequency domain, I guess. But it basically, yeah, it's going to determine more or less the number of resonances we have, how strong they are, and more importantly, how strongly we couple to those resonances when we buzz into the mouthpiece. And so, yeah, that's what determines like the tone of the noise. It's the distribution of those harmonics. And so the question is, why did I bring this up? Because I was talking about crystallography. Well, it turns out exactly the same principle can be used to describe anything that's periodic. That's why Joseph Fourier came up with this. It's nice to think about it in terms of sound waves, because we can literally hear differences between various things, but that's not all that's going on. That's not the only place this is actually relevant. Do I have my power cable near? Yes, I do. Let's plug in the power. Stop doing this. Okay, power's on. Yeah, and so basically the reason Fourier came up with this was because he wanted to describe a particular periodic function and write it in a particularly neat way, and it worked. And the thing is, you can use this for lots more periodic problems, including periodic problems involving a lattice. Let's lure this. Oh, wait a second, I can try something actually far bigger brain than I've tried in the past. Because these guys I can lure for ages. Probably lure this guy all the way over here. And I think I can just then beat the Admiral in the time it takes to get back to me. Or at least do a good amount of the damage. Because I don't want to... I won't beat it, but it'll be close. I might do. Quickly. There we are. That's perfect. Then I can lure this guy over here. And I won't have to deal with that initial starting rush. And I also don't have to risk fighting the Admiral whilst also fighting a Stroming Pirate, whilst also trying to keep the Stroming Pirate alive, whilst also trying not to get hit by the Admiral. You can see why I dislike that method. But yeah, so basically, we can do all of this, and we can basically determine, like Fourier's analysis also allows us to determine largely whether or not things are going to be insulating or conducting. Do we not have any max? Okay, no max. Cool. So in particular, this Fourier analysis allows us to calculate these band gaps, and these band gaps will calculate, depending on how where electrons are relative to them, they'll tell you whether or not you've got something that's conducting or something that's insulating. Now, the interesting part of all of this is that basically quasi-crystals or aperiodic structures in general, you can have long-range order, but you can have no periodicity. But your issue is, when you try and describe this, well, wait a second, all of the techniques I use are based around Fourier series, Fourier expansions. If I don't have those, what do I have? At which point Joseph Fourier turns to you and says, if you're nothing without this expansion, then you shouldn't have it. But anyway. Oh, okay. Got you as well. That's annoying. Do I beat this in time? Yes, I do. It's lucky. But yeah, and so the question is, how do you do this? And basically, yeah, I had a really good time giving this talk, because I really enjoy teaching teaching physics. Which probably, I mean, okay, it probably comes across that I enjoy it on this channel. It probably doesn't come across that I have any competency whatsoever, because it's so much harder to teach physics without drawing diagrams, which is what I... Which is, whenever I'm talking about physics on here, I'm more or less trying to teach physics without drawing anything, so I have to describe everything with words, and physics needs diagrams. If anyone tries to teach you physics without diagrams, something's gone wrong. Equations as well. Equations are nice. But that's just because equations draw diagrams succinctly. Get you aggroed. Yeah, so yeah, basically I can then I can try and analyze quasi crystals, but it's really, really difficult. And so it turns out, and so yeah, I was basically giving a talk on, okay, what are the methods we actually use to analyze these? Because I think that's a really, really interesting question. Nothing we have works to analyze them. So how can we do maths on them? And it turns out they have some cool mathematical properties. I don't know if they have any cool physical properties, if I'm honest. I've yet to see something from them which, like, I look at physically and I think, okay, this is really cool. This, like, you couldn't get this any other way. Turns out most of the time they just tend to share their properties with somewhat disordered materials. So they tend to have quite similar properties to, say, glasses, for instance. Which is not the most interesting thing in the world. Great, I played myself. Hopefully I can smash this guy. Okay. Oh, that's fine, I can pull that. I guess I could, yeah. I can just pull that Admiral over here. Not Admiral, Pirate, you know what I mean. Come on, you've got a de-aggro soon. Come on. How are you still aggro? Okay. Yeah. But yeah, and so I was giving a talk on that as part of this, and yeah, it's really interesting. There are people have come up with really, really cool ways of understanding these crystals, and like the best part is that, like, the way we tend to understand them specifically involves higher dimensions. Like, that's the neatest way we have of describing these things, which means that a lot of the properties, like, we basically, so if I take the simplest example of a one-dimensional quasi-crystal, say the Fibonacci chain, if I want to analyze this, I need to go, more or less, to a higher dimensional space and do the maths there. And what this gives rise to is quite often properties which look as though I'm in a higher dimension, despite the fact that, no, this quasi-crystal does only exist in 3D. This isn't a time crystal or anything like that. If you've seen those, it's completely unrelated. It's, yeah, has no higher dimensional properties whatsoever, but it sometimes looks like it does because it's defined with a higher dimensional, or the lattice seems to be almost higher dimensional. This is going to be tight. I really should just be retreating at about this stage. I'm going to do that. It's annoying, but it will also keep me alive. A little bit of a waste of time there, but ah well. Right, let's try this again. Hello. Okay, that was not what you were meant to do, but you know, we'll go with that. Did I just run away too quickly? I probably did. And now I'm at the wrong point. Cycle relative to the health I have. Annoying. What is going on? This is the most scuffed fight ever. Yeah, honestly, this round is the most scuffed round ever. Nothing in this kind of went well. No, 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 no. I guess it was fitting with the way everything else went that fight went like that. I guess I shouldn't be surprised. Um, yeah, so it turns out that, like, yeah, when you do the maths for this, it seems like almost necessarily higher dimensional, and like all this analysis, and this gives, and you get like really weird fractal structures. Do they actually have any like practical use? Probably no more than glasses do. Um, I really have yet to see any behavior which like, kind of like really strikes me as, hey, this isn't just glass. But you know, they do have long range order, so like there is always the potential. And yeah, you do get things called phasons. I'm not 100%. I haven't spent much time looking at the experimental data for them, so I'm no expert on them. But I'm not thoroughly convinced. By like, I obviously I believe they exist. I don't know how useful they actually are, or to what extent they are. So they're like one of the things peculiar to Quasi Crystals, that they have these phase-on modes. Seriously? Okay, for starters, I think I hit that cherry fast enough. Um, Secondly, I'm amazed that didn't count. Okay, I'm also gonna, I think, swap around and do some other testing for a bit. Um, that was not what I intended on doing. Don't know what I plan on doing. I'm just gonna look around for cool stuff, I guess. I could spend even more time investigating the bug. I don't know the bug state. I don't know. I want to do that to myself. But yeah, so that was the somewhat interesting thing recently. Yeah. So how do I describe these? So yeah, you've got these phasons, which are they do exist. They're basically, turns out, as well as like phonon modes, which are like way sound waves travel. You do also have these phazon modes, which are basically, they they're like they almost represent this motion in a high dimensional space, which is really cool, really interesting. It's just interesting to note that yeah, no amount of walking forwards actually prevents this, which is very similar to when you're out of control whilst sliding off of something, whilst falling. Seems related. Yeah, I've no idea if these phase-on modes actually provide anything useful. They seem like the the one point where, okay, quasi crystals have this, other things don't have this. Are they actually useful? I don't really know. Um, some results have apparently claimed they move faster than sound speed. I am incredibly suspicious of that, because the thing is, the way information travels on a lattice is almost always phonons. You need to have, like, in order to know that something about the lattice has changed, vibrations need to travel from one point on the lattice to another. Saying that these waves travel faster than phonons seems incredibly dubious. I've no idea what I'm doing right now. Okay, let's take a look at. I've done this before, but just going to take a look at the loft areas. I might give myself. It'd be really hard to give myself all this. There's probably a macro to give myself all the Ninjago tasks, or the Ninjago missions completed. feeling lucky. What's that one? Nice. Oh! Wait a second, yeah, if I want an area to test weird friction values... I'd completely forgotten this existed. Wait a second, this is like... This is... okay, I'm really glad I came over here. Do we have an area? We have a single one of... Yes, we do. Over there. Okay, cool. So I'm going to try and do now. Guess I need to spawn an Admiral somewhere. At some point, but what I'm going to do now is I'm going to fold repeatedly. Probably. Where do I spawn the Admiral? Spawn it over here. Hopefully I'll be outside the aggro range. If I can achieve this over here, that would be huge. Nothing suggests to me, honestly, yet that it will be possible, but, you know, I can hope. I'm just going to run away. Well, I guess I might as well try first. Although we know I'm incredibly inconsistent with this trick. Wait a second. Was that just good timing? That may have been good timing, or it may have been I just badly timed that ground pound. Didn't even ground pound there. I did, I'd like sky on level floor. Guess I can do it up here. Did I get into the bug state? I think I have. I don't know if I ground pounded in time there. I did. I'm in the bugged state. I'm in the bugged state without... We've got a model for the bugged state. Ladies and gentlemen. Got somewhere we can... Not only we've got the bug state, we can reproduce the bug state, and I can clearly see the physics object I'm looking at, which is huge, because that's the reason doing all of this has been so difficult, is being the fact that I can't see the physics object. So we triggered it by ground pounding, falling off the one edge. Specifically, I think it was being on the other sides that caused it. Now let's... Same again. I don't know why I really expect there to be any difference, but... Okay, that's actually a more repeatable way of doing this. So we've... okay, this is cool. So for starters, a more consistent setup to getting a bug jump off of an Admiral. But secondly, we've got a bug jump with in an area which has different physics. This is huge! Whew. Oh, I'm incredibly excited about this. So we can enter the bugged state with completely different physics from the physics I would normally use to enter it, or in a completely different area. And the fact that this is possible, this bodes really well for getting this elsewhere. So if we can work out what's causing this here, we can do a little bit of science, see, we can maybe find out where else this is possible. Again, does it have any uses? Don't know. Right now, I'm doing science for science's sake with this. Okay. So what do I want to try? First off, let's try remaining on this side. Not expecting this to work, but never know. Did not work. Cool. You need to buff me. Well, firstly, let's see if I can repeatedly enter the bug state like this. I guess that's a good first thing to look at. Okay. Don't think that was it. I don't think we're in it. No, definitely not. Actually, let's just see if I can get high enough. No, I know I can't. It's not high enough up. Honestly, strong admirals are like the easiest enemy to defeat with your fists. I think. Okay. At least for their health value. Because I mean, I guess strong ones are easier, but... That I don't expect to have worked, but... No, it did not. Nope. Although that last one looks more or less perfect from what I would expect to cause it. What just happened? I'm confused. Okay. Seems the one rule with getting this glitch is you need beginner's luck. Also, note one important thing which I didn't mention: the friction here is much, much less than it is, or the I guess the frictionlessness. No, and we seem to have much more friction than we do in Old Forest. Alright, I mean, somewhat enjoying the dichotomy of me claiming I have a consistent setup now, and me utterly failing to achieve it consistently, but it's fine. Okay, that was definitely a failure though, so it's good. I'm amazed I made that. Kind of wasn't expecting to. Also, yeah, what is it with this trick and getting it first time and then not being able to replicate it after first time? I can't just have hit all those jumps with perfect timing earlier. That's not possible. You note how quickly I go back to instantly doubting myself with this, but no, I'm not wrong. And for anyone wondering how I landed in midair there, you can attack again whilst in midair, and it cancels your ground pound past a certain delay, which is related to the amount of time you're stunned for. Why do I should just keep this equipped? The reason I unequipped it was because it might risk breaking something, but I think we're probably good. Why did I take that off there? Small brained even by my standards. I'm not saying something. Nope. That makes things faster. Do not want to do that. Could also do a teleport up there. Might not be a terrible idea. Nice colouring on this. Yeah, I'm pretty. Yeah, that wasn't a success. Oops. It's odd that I've not been able to do this again. So let's. Why did that not? Oh, that was weird. So I came up here, explored around, noticed that, went to it, ground pounded. And got the bug. There we are. What did I do differently? This is interesting. This is quite exciting. So something I did in going up that way that I didn't do. Could it be the... Could it be related to me flying up? That's interesting. And like again, we can in this area we can see the physics. This is so much more repeatable. Oh, I'm very, very excited. I don't know what's going on. I don't know why what's going on is going on. I don't know if it has any use. But we've got something weird happening, and I love it. Don't want you. Don't want this. I don't want... Okay, so let's see happens if I land up here after the bouncer? Let's see if it's related to the bouncer. Let's do that as a first test. Can I just spawn in that parrot thing? Interesting. Okay, no bug. I think that was a fall without a bug, but let's just double check. Fairly certain I trust us and my memories, but yeah. Okay, cool. So we didn't manage that. I'm now going to take the bouncer. The more steps we add to this setup, the weirder it gets. Okay, does it require the bouncer? That might explain. That might explain some stuff. So is there something that gets... So some weirdness is going on with the bouncer. The only annoying thing is that setup... The setup is now multi-step enough that it actually could potentially be related to server input. Be related to the server. If I've spent all this time investigating something which just turns out to be a server-side glitch, I'm actually going to be quite annoyed. But well. I can live with that annoyance. Okay, so we are in the bug state at the moment. Let's confirm one last time. There we are. Cool. So it seems we need to have at some point used the bouncer. Okay, does it matter which bouncer now is the next question? Well, no, I guess I should try it again without using any bouncer. I feel this is honestly at this stage, this is one of those things that cheat engine would just be incredibly useful for. I don't know much about how it works, but I'm assuming you can like narrow down. Like if I recall correctly, cheat engine works by like following variables in memory. Following the memory associated with the program, and like you can narrow down which parts are changing, which parts aren't. So that's 6 damage from a single Stroming Admiral. That's chunky. Okay, no bug. Now let's do this and see if we get a bug. Actually, no. Let's not do that. Let's do this. probably missed it, but you know, let's try. Like, we don't know what causes it. Maybe it will also work like that. I don't know. That did work. Finally, some progress on this. Woo! I apologise if I said that, if I shouted woo a little bit too loudly there, because I did literally just shout woo. Okay, that's cool. Oh, we're making tons of progress. This is good. So we now know we can achieve this off of both sides of the thing, which is really interesting. So that suggests it doesn't seem to, we know it's working with higher friction values. Okay, let's just double check that the whole... Okay, I'm just going to go around, but I'm then going to jump off of something wooden. Try it again. Hey there. Has this been a red herring the whole time? Oh no. Oh no. Oh no. Oh no. Please tell me this is not what I think it is. Well, okay, let's do some more testing. Let's try something different this time. It could also... I should have done one more test last time, actually. Didn't think about that. Okay. So now I'm literally just going to jump off here, because last time I did barely anything but jump on a bouncer. And the bouncer seems to be required. So maybe it is just the bouncer. It is, in fact... well, at least it seems to be just the bouncer. Oh, no. Oh, so was that whole thing a red herring? I think it was. I can't believe that. I've spent days trying to track down this bug. And it was literally just a bouncer. Nothing to do with friction values. Nothing going on with that whatsoever. It was just a bouncer all along. I'm slightly interested in the fact that I didn't land the attack there. But yeah, okay. It's literally a bouncer. That whole thing was a red herring. I was not jumping in a specific spot which was causing this. It's just that quite often in testing, in order to get to that spot, I had to jump on a bouncer. There was never anything special about it whatsoever. Oh no! I wasted so much time trying to hunt that down. Oh. Oh, that's hilarious. So yeah, all along, nothing... Waiting, does that 100% track? Maybe it's not just bouncers that cause this. Regardless, I seem to be able to achieve it with just a bouncer. I think I've achieved it before without using a bouncer, though. But regardless, I don't really care, I don't think. And I wanted if using a lantern would reset it. Like, there's no good reason why it should, but you never know. So I'm going to give this one more test. And if this does turn out that it is literally just a bouncer, I'm going to call this a success. I mean, it will have been a success. But, I think it'll be very fair to call this a success if this does work. With just about, like, at least I know what was going on. But yeah, how's that for... no, I still on ice. It didn't want to do that. I guess there's... Can I make that? I don't think I can. Yeah. Doesn't matter too much, because we're now fairly certain it's not the ice. This actually... I'm still like, I can't believe this is what it is. But yeah, there we are. It was a bouncer all along. Oh, the annoying thing is that could actually be server-sided. That could be a server-sided error. I don't know. So I will actually have to take a look at that then. Because bouncers, that seems very plausible. So yeah, so okay. So here's where the theorizing begins. I mean, okay, for starters, useful. We can get this in any world now. I also wonder how this combines with the existing bouncer ground pound bug, because those two, like, now we know those two are like really, really related. Those went from being completely unrelated bugs to wait, no, these are fundamentally linked. So much of them being different. But I thought the common factor was air movements being weird in both of those, because we know air movements are normally weird, but it's not. Oh, that's... I can't believe that. That's hilarious. Again, we still don't have much of a use for this. Did I get the state on here? I don't remember if I've already given myself it. So I guess there's other stuff I need to test as well. Okay, I've given myself the state. So let's quickly relog again. Get rid of it. And then I'm going to head over and use some other bouncers. Just to see... We're trying to narrow down what's going on. Maybe that will make a difference. I don't know. But I can't... But, I mean, they are... Just how much of a red herring that was. Oh yeah, I guess check it if anything else can trigger it. So the reason I suspect bouncers work in some sense. Wait a second. Bouncers and all of these other things knock you back in quite similar ways. No, no, okay, I know admirals don't cause it, though. I know admirals can't cause it. Because I have been, in testing lots of times in the past, I have been smashed by admirals. I have done stuff with admirals. And then attempted it again. So, okay, I know for a fact that admirals can't cause it. That would actually be so incredibly cyclic if they could, so no, I know for a fact that doesn't happen. Okay, so I'm just gonna... like, nothing should happen with these lanterns, but you know what? I'm gonna try it anyway. Nope. Slightly confused lantern, but alright. And, okay, so we know what's causing it now. We know what's causing it. We can repeat it somewhat reliably. I guess, yeah, I'll need to talk with the devs. I talked to Zypho about this already. He suggested I Wireshark it up. The issue was you'd have to Wireshark it up from the beginning of the session, and I'm not 100% comfortable with that on most servers because that would involve then me giving away my password potentially. Let's do this very quickly because I remember this being incredibly difficult for me as a kid, and I just want to do it very quickly now. Just to show off how much of a gamer I am. I can't believe that was it. So bad. Okay, I'm also, yeah, I guess I'll go into one of the other dojos at the end and then test, once I've done this, and test it out. So I've been told it's possible to do this without building, apparently not that quick build. So I'm going to try and make the jump. In original tests, hasn't managed it, but apparently this is doable. Not like that, it isn't. Can I make it back up before it runs out? Yeah, I can. Been told that is doable. I'm not going to spend too much time looking for it now because I'm not really interested in that for the moment. Because that's a precise jump. It's not, to my knowledge, there's not like any particularly interesting tech with it. Aside from the fact that it's just cool that you can happen to make it. And the fact that I still have never made it. Yes, in case you're wondering, what I am doing right now is literally 100% a flex on childhood me. Okay. Alright, I just got a message from my friend who's also going to this lesson with me, so I will I'll probably head off shortly. But yeah, thank you very much for watching. We did it. Let's test this, but I mean, I'm expecting it to work. I'd be really surprised if it didn't. Might give me more information if it didn't, but you know what? I'm edgy. If I don't manage, I will be knocked off, probably. Okay, let's maybe try this down here. Not getting the jump off in time. There we are. It was bouncers all along. Thank you very much for watching. I've been Ninja You. See you around. I can't believe that. Bye.